Okay, so if a function's runtime is greater or equal to than the smallest possible linear function, then it could also be less than or equal to large possible quadratic function. In this case, that would be true because all big omega of n is saying is that it's greater than or equal to linear, and then all O of n squared is saying it's that it's less than. So it could be greater than linear, but that also means that it could be less than quadratic. If a function is in between the smallest linear function's runtime is between the smallest linear function and the largest linear function, then could it also be smaller than the largest quadratic function? That would be true, again, because all big theta of n is saying is that it's it's between these bounds of a linear function, but that also means that you could say that is smaller than n squared. And then if a function is greater than the smallest linear function, then it is always less than the the largest linear function. In this case, it would be false because what omega of n is saying is that it can be any function that is greater than the runtime is anything that is greater than linear. That doesn't necessarily mean it is always less than large linear. It could be quadratic, it could be exponential. It could be factorial. It could be a lot of other things. It doesn't necessarily mean it's always less than the largest linear function. So this would just be false. Okay, so suppose someone ran a sorting algorithm on an array of 8 integers. We don't know the exact sorting algorithm was used, but we do know the order of one array at one point in time during sorting. So the initial input is this, and during sorting is this, and then it can either be selection sort, insertion sort, or merge sort. So we can try each one out. So first, starting with selection sort, we have 0, and then we check the minimum so far, and in the array, and that would be 0. Okay, so that's fine. And then we have 4, and then we swap it with the minimum, and that would be 1. But during sorting, it goes 0, 2. Okay, so it can't be selection sort. Okay, now we can try insertion sort. Insertion sort, you have you're starting with 0, and then okay, so you have 0, and then you go to 4, and then you need to insert that into the right spot. So 0, 4. Okay, then you have 2, and then now you insert that into the right spot. Okay, 0, 2, 4. Then you have 7. Okay, you need to insert that to the right spot. 0, 2, 4, 7. Okay, so everything looks good. And then you have 6, you need to insert that to the right spot. Okay, so now it needs to be 0, 2, 4, 6, 7. In this case, it wouldn't be correct because during sorting, this is how it looked. Okay, and we know that because, well, 1 and 6 have obviously moved, and obviously if it was insertion sort, then 6 would have moved before the 7. Okay, so we know it's merge sort, but we can just check to see. Okay, so merge sort, you have to sort the left hand side and sort the right hand side and then merge them. So you start with the left hand side, and then you just go to the left hand side again. 0, 4 sorted, 2, 7 sorted. Those two merge are 0, 2, 4, 7, just like this. And then now, you go to the right hand side. Okay, now you sort the left hand side, and I have 1, 6. And then you sort the right hand side of 3, 5, and there you go. It'll be a merge sort. Okay, consider this method G that takes two arguments, a goal and step size, and then perform asymptotic runtime analysis for G of n and 1 with respect to n. So essentially what's going on is that it's going to loop through and print out steps of G, starting with step of 1, and steps of the goal, starting with 1. So at first, we had to give a recurrence relation t of n, describing the runtime of g of n1 with respect to n. So at first, t of n, I'm going to look at the non-recursive part, at t of n1 would just be equal to n, because you have to loop through the whole number of that being n, the whole goal. And then this is the way that the recursive works. So now you have the same goal, but you're multiplying steps times 2. So that means instead of going 1 now, you're going by 2. And then after that, instead of going by 2, you're going by 4. So what essentially that means is that, the number of steps you have to take 2g to the goal essentially goes down by half, because the steps doubles. So really what's going to happen is that for this function, this recursive part, you're going to get t of n divided by 2, and since there are two recursive functions, it's going to be 2t n divided by 2.